own unique vibrational frequency, like a cosmic fingerprint. What if you could actually tune into that frequency, pinpoint your exact location, maybe even navigate across the stars just by listening? It's a pretty wild idea, right? And it's this profound, captivating idea we're going to explore today. We spent some time poring over a stack of sources that really dig into this concept, this vibrational positioning. They look at the theory behind it. Is it even plausible? Could it be more than just science fiction? It's quite a journey, really. Takes us from the absolute smallest quantum fluctuations right up to the grandest cosmic ripples. So our mission for this deep dive is to, well, rigorously scrutinize this whole idea through the lens of modern physics. We'll try to unpack what vibration actually means in different scientific contexts and whether a point can even exist as we normally think of it, and what it would genuinely take to build such an incredible navigation system.
Yeah, it's fascinating, isn't it? Because this idea, it sounds speculative, maybe even fringe, but it forces us to grapple with some of the deepest concepts we have in physics. It really pushes against our everyday intuitions, makes us think about reality in completely new ways.
Harry, so buckle up, everyone. We're about to tune into what some sources call the universal symphony. Let's start with the core idea, vibration. When physicists talk about vibration, it's a lot more involved than just something shaking back and forth. Our sources seem to reveal like three distinct layers to this universal symphony.
That's right. The first instrument, you could say, and maybe the most fundamental, is quantum field theory, QFT. In QFT, reality isn't built from little particles like billiard balls. It's made of continuous fields that permeate all of space and time.
Okay, fields, not particles.
Exactly. Think of an electron. It's not a tiny ball. It's more like a localized excitation, a temporary ripple or vibration in the electron field itself. It's sort of like plucking a guitar string. The whole field is the string of the instrument, and the particle is the note you hear, the vibration.
Okay, that makes sense. But what about empty space then? If it's all fields, what's happening where there are no particles? The sources mentioned something interesting there.
Yes. Empty space in QFT is, well, anything but empty. It's the ground state, the lowest energy state of all these quantum fields. And it's incredibly active. A turbulent quantum foam is one description. Virtual particle-antiparticle pairs are constantly popping into existence and annihilating each other.
So it's like a constant background noise.
Precisely. It creates this ubiquitous cosmic hiss, a baseline of vibration everywhere in spacetime. And it's not just theoretical, we can actually see its effects. The Casimir effect, for instance, this tiny measurable force between two uncharged metal plates in a vacuum that's a direct result of this quantum foam altering the vacuum energy between them.
Wow, okay, so the universe is inherently noisy, vibrating.
You could say that. And the key insight here is that it's a dynamic, interactive medium. A particle, like our electron example, doesn't just sit there. Its presence actively perturbs the fields around it, like the electromagnetic field, which is what gives it charge. So any location's vibrational state isn't just a single note or a simple sum of waves. It's this incredibly complex, dynamically interacting state, constantly shaped by everything around it, a living hum.
All right, so that's QFT. What's the second instrument in this symphony? You mentioned string theory earlier.
Right, string theory. This proposes an even, well, deeper layer. It suggests the fundamental building blocks aren't particles, or even those field excitations we just talked about, but these unimaginably tiny, one-dimensional filaments of energy, vibrating strings.
The classic violin string analogy, right? Different vibrations give different particles.
Right. That's the popular analogy, yeah. And it's powerful because different vibrational modes could theoretically correspond to different fundamental particles, electrons, quarks, photons. It aims to unify that whole particle zoo. And importantly, it naturally seems to include a vibration that corresponds to the graviton, the quantum particle of gravity.
Which is a huge deal for unifying physics. But hang on, you mentioned earlier that particles are low-energy things compared to the scales physics deals with. Does string theory explain how we get, regular low-mass particles like electrons from these vibrating strings? Doesn't vibrating something take energy?
That is an excellent question, and it points to a crucial detail often glossed over. You're right. To make a fundamental string vibrate significantly in a way that corresponds to its basic harmonics actually requires immense energy. We're talking energies approaching the Planck scale. So the particles produced would have enormous masses, like 10 to the power of 19 times a proton's mass. Clearly not our everyday particles.
So how does string theory explain the particles we actually see, the light ones?
It relies on much more subtle and complex mechanisms. Things like supersymmetry. which proposes a symmetry between different types of particles that could cancel out some energy. Or compactification, the idea that there are extra spatial dimensions curled up incredibly small, and the geometry of those hidden dimensions affects how the strings can vibrate, allowing for lower energy states. And also branes, these are higher dimensional surfaces or objects that strings can be attached to, which also changes their properties.
Okay, so it's way more complicated than just plucking a tiny string.
Absolutely. A vibrational signature in string theory, if it's correct, wouldn't be a simple tone. It would be this extraordinarily complex thing encoding not just the string's own vibration, but how it's moving and interacting within these hidden dimensions and structures. Far from simple.
Right. Okay, QFT, string theory. What's the third big instrument?
The biggest one, in a sense, general relativity, Einstein's theory of gravity.
Where gravity isn't a force pulling things, but the shape of space-time itself bending?
Exactly. Massive objects warp space-time around them. And crucially, when these massive objects accelerate, think merging black holes, colliding neutron stars, they create propagating disturbances in space-time. These are gravitational waves.
And unlike light waves, which are vibrations in the electromagnetic field.
Gravitational waves are vibrations of space-time itself, ripples in the actual fabric of reality. They're usually at much lower frequencies than light too because they come from accelerating masses, not charges.
And didn't recent discoveries confirm there's a background hum of these two?
Yes, the stochastic gravitational wave background. It's like a persistent cosmic hum from countless events throughout the universe's history, merging supermassive black holes, maybe even echoes from the Big Bang. Pulsar timing arrays, these networks of incredibly precise cosmic clocks, have recently found compelling evidence for this low-frequency rumble. It confirms spacetime is constantly, subtly in motion, alive with vibration, you might say.
So let's pull this all together. At any given location in spacetime, what's the overall picture?
You've got the high-frequency quantum jitters from the vacuum fields of QFT. You might have the incredibly complex modes of vibrating strings interacting with hidden dimensions, if string theory pans out. And you definitely have the large-scale, lower-frequency ripples of space-time itself from general relativity, both the background hum and passing waves from specific events.
So it's not one frequency at all, it's a mess.
A dissonant superposition, as some sources put it. A truly complex, multi-scale vibrational state, not a simple, single frequency you can just tune into like a radio station.
That's a huge takeaway right there. The universe's vibration is a complex orchestra, maybe even a bit chaotic, definitely not a solo performance. Okay, so that brings us to part 2. Let's really tackle the core premise of vibrational positioning, that every point in space-time has a unique vibrational frequency. Oh, we've already seen the frequency part is complicated. What about the point part? Our sources suggest that's also problematic.
Deeply problematic, yes. We have to ask, what even is a point in physics? Classically, sure, it's a location with 0 dimensions. Simple. But quantum mechanics throws a major wrench in that. Heisenberg's uncertainty principle, the HUP.
Right. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa.
Exactly. And it implies that to perfectly localize something at a mathematical point, to know its position with infinite precision, would require infinite energy, which is, well, physically impossible.
So points don't really exist in a quantum world.
At the fundamental level, the concept breaks down. At the incredibly tiny Planck lengths, about 1035 meters, the quantum fluctuations we talked about become so extreme that space-time itself isn't smooth anymore. It's thought to be this chaotic quantum foam where our usual notions of distance and even duration start to lose their meaning. The idea of a precise point becomes fuzzy, probabilistic.
And relativity adds another layer of complexity, doesn't it, with coordinates being observer-dependent.
It does. Your measurement of location depends on your own motion and gravitational environment. And in extreme cases, like inside a black hole singularity, our understanding of points and locations breaks down completely.
So if a point isn't really a point, and the frequency isn't really a single frequency, where does that leave the original idea? Is it just dead in the water?
Well, we have to adapt. To even continue the discussion meaningfully, we need to reformulate the premise, as the sources suggest. Instead of a point, maybe we should talk about a minimal resolvable space-time volume, the smallest chunk of space-time where physics still makes sense. And instead of a unique frequency, we talk about a characteristic vibrational signature, that complex multi-layered cacophony we discussed earlier.
Okay, a minimal volume with a characteristic signature. That sounds slightly more plausible, maybe. but still incredibly complex.
Vastly more complex. It shifts the whole thing from a neat classical idea into a really messy quantum and relativistic challenge.
So let's accept that reformulation for a moment. What would this characteristic vibrational signature actually contain? If we put our hypothetical cosmic microphone in that minimal volume.
Okay, what would it pick up? First, that constant high-frequency hiss from the quantum vacuum fluctuations. That's your baseline noise floor.
Then maybe the notes of actual particles passing through.
Exactly. Any real particles whizzing through that volume would add their specific energy signatures to the mix. Distinct notes over the hiss.
And the gravitational wave background.
Yeah, that persistent low-frequency rumble from all those cosmic events. A deep hum underneath everything else.
Plus any big transient gravitational waves passing by, like from a black hole merger.
Right, those would be like sudden loud chords sweeping through the signature, powerful but temporary additions to the spectrum.
So it really is a cacophony.
An absolute cacophony. An extraordinarily complex interference pattern of all these different phenomena playing out simultaneously.
But could that cacophony still be unique to the location?
That's the hope of the premise, right?
Yeah.
The uniqueness wouldn't be in a single frequency, but in this specific combination, the phasing, the relative amplitudes of all those components. It would essentially be, as one source puts it, a kind of holographic record of its entire causal past, everything that has influenced that little patch of space-time.
But then you had a massive practical problem, don't you? The noise.
A monumental signal-to-noise problem. We mentioned the Casimir effect showing the vacuum has energy. Theoretical calculations of the vacuum energy density are, well, they're famously huge.
Huh.
Some estimates go up to 100 and 113 joules per cubic meter. That's an almost inconceivable amount of background energy, background noise. Trying to distinguish a subtle location-dependent variation within that overwhelming background. It's like trying to hear a pin drop during a supernova. The difficulty is just staggering.
Okay, and we also touched on the idea that even if you could measure this signature, the frequency aspect is tricky because it's relative.
Yes, that's another fundamental issue. Any complex vibration like this space-time signature won't be a single frequency. It'll be a broad power spectrum, a distribution of energy across many different frequencies.
Like listening to an orchestra versus a tuning fork.
Exactly. And crucially, what frequencies you measure depend on you, the observer. The Doppler effect shifts frequencies based on your motion relative to the source. And general relativity adds gravitational redshift frequencies change depending on the strength of the gravity field you're in. So your measured signature changes based on where you are and how you're moving.
So a navigation system based on simple resonance seems, well, impossible then. How do you resonate with something that isn't a fixed frequency and changes depending on you?
It makes the idea of resonance, like tuning a radio to a specific station, incredibly difficult, if not meaningless in this context. If the target signature is this broad, dynamic, observer-dependent spectrum, what are you actually tuning to?
This is where the sources suggest reframing it again, right? Away from frequency and towards information.
Precisely. A single frequency carries very little information, but a complex spectrum, like the one we're describing, that potentially carries an enormous amount of information. So maybe the hypothetical system isn't really a tuner. It's better understood as an incredibly sophisticated information matching system.
Like a computer that could somehow record the signature of a target location, say Mars, and then compare it in real time to the complex signature of its current location.
Something like that. It shifts the problem from simple resonance physics to the realm of quantum information theory and extreme computation. A monumental shift in concept.
Okay, let's shift gears again. Part 3. Let's actually try to imagine building this thing, this vibrational positioning system, or maybe vibrational information matching system. Where do we even start? The sources suggest looking at our best current technology for resonant detection. Atomic clocks.
Good starting point. Atomic clocks, like the cesium fountain clocks that define our second, are marvels of engineering. They work by exploiting the incredibly stable and predictable resonant frequency of electrons transitioning between energy levels in specific atoms. For cesium-133, that frequency is precisely 9,192,631,770 hertz. Like Incredibly precise. They use sophisticated laser cooling and microwave interrogation in a feedback loop to lock onto this natural, stable atomic resonance.
Okay, so super stable, super predictable, single frequency. But based on everything we've just said, that model completely fails for trying to detect a space-time resonance, right?
Completely, because that characteristic vibrational signature of the spacetime volume is none of those things. It's not stable, it's dynamic, it's not predictable in a simple way, it's chaotic, and it's definitely not a single frequency, it's a complex, noisy power spectrum.
And it's observer dependent.
And observer dependent. So there's simply no stable note to lock onto like there is with an atom. The atomic clock analogy breaks down immediately.
Plus, there's that other huge issue you mentioned earlier, the mapping problem.
Ah, yes, the bootstrapping problem.
Yeah.
It's a killer. For your spaceship to navigate to Mars using this method, it somehow needs to already possess the unique vibrational signature of Mars.
How would it get that information?
Well, either you'd need a perfect simulation of the entire universe, factoring in every quantum fluctuation in gravitational waves since the Big Bang to predict Mars's signature, which is computationally impossible, or you'd need a vast network of probes that have already been everywhere, including Mars, measured the local signatures, and stored them in some universal database your ship can access.
So the navigation system requires you to have already solved navigation to build the map it needs to navigate.
Exactly. It's a fundamental circular logic problem. You need the solution before you can even start.
Okay, what about the other part of the original idea, not just detecting, but somehow fine-tuning the vibrational frequency of the spaceship itself to match its destination?
Right, this implies something truly extraordinary, macroscopic quantum state engineering. It means taking an object made of trillions upon trillions of atoms, like a spaceship, and somehow controlling its overall quantum state with exquisite precision, putting it into a specific, coherent vibrational mode.
We can control quantum states now, can't we? With lasers and things.
We can, but on a vastly smaller scale. Using lasers, magnetic fields, the techniques of quantum computing, we have achieved remarkable control over individual atoms, or maybe small collections of atoms like ions in a trap. But crucially, this is almost always done under extreme laboratory conditions. Ultra-high vacuum, temperatures near absolute zero, heavy shielding.
Why the extreme conditions?
This prevents decoherence. That's the killer for quantum effects.
Yeah.
Any interaction with the surrounding environment, a stray photon, a gas molecule, even the object's own internal heat can disrupt the delicate quantum state and make it collapse back into a classical state. The quantum vibration gets washed out by noise.
And trying to do that for a whole spaceship.
The mismatch in scale is just mind-boggling. Imagine trying to get every single atom in a multi-ton spacecraft to vibrate in perfect quantum unison. The energy required would be astronomical. And maintaining that coherence in a warm, complex, inherently noisy environment like a functioning spaceship, it seems fundamentally impossible according to our current understanding of physics. Decoherence would destroy the state almost instantly.
So the sources argue the spaceship itself is the wrong thing to tune. You'd need an incredibly sensitive detector on the ship.
Exactly. The focus shouldn't be on manipulating the ship, but on building a detector capable of sensing those incredibly faint, complex spacetime signatures, perfectly shielded from all the noise generated by the ship itself. Engines, computers, life support, everything. Another monumental engineering challenge.
Okay, so let's put this hypothetical VPS into context. How does it stack up against navigation we actually use, like GPS, or things that are at least theoretically plausible, like quantum positioning systems?
Well, GPS, as we know, is classical. It relies on timing signals from orbiting satellites using radio waves. Its weaknesses are things like signal blockage, tunnels, buildings, deliberate jamming, or even spoofing with fake signals.
Still works pretty well most of the time, though.
Oh, absolutely. It's a mature technology. Now, quantum positioning systems, or QPS, are still largely theoretical, but are grounded in known physics principles. They might involve using networks of entangled particles, perhaps photons, distributed in space. By making measurements on these entangled particles, you could potentially determine positions with very high precision, maybe overcoming some GPS limitations. But even QPS faces enormous technical hurdles. Creating and maintaining entanglement over large distances is incredibly difficult. Decoherence is still a problem, and the infrastructure would likely be hugely expensive.
So QPS is hard, but maybe possible. Where does that leave VPS, this vibrational system?
VPS seems to be in a different category altogether. The sources really highlight its unique and, frankly, arguably insurmountable challenges. First, the problem of even defining what the signal is, this complex, noisy, observer-dependent signature. Second, the challenge of detecting that whisper against the roar of the quantum vacuum and local noise. Third, the bootstrapping problem of mapping these signatures. And fourth, the sheer fantasy involved in engineering either a macroscopic quantum tuner or an impossibly sensitive detector.
It sounds like it's not just hard, it relies on principles that might fundamentally contradict what we know about physics.
That seems to be the conclusion from the sources, yes. It bumps up against the uncertainty principle, relativity, the nature of quantum fields, decoherence, and the signal-to-noise limits in fundamental ways.
Okay. So, wrapping this deep dive up, it seems the idea of vibrational positioning, while it sounds amazing, just hits roadblock after roadblock. We're not just talking about needing better technology. We're talking fundamental contradictions with physics as we understand it.
I think that's a fair summary. The root issue seems to be the classical intuition baked into the original query. Modern physics just doesn't work that way. Points are fuzzy and probabilistic. Frequencies are complex spectra and observer-dependent. Spacetime's signature is a chaotic cacophony dominated by vacuum noise, not a clean signal. The mapping creates that logical loop. And the engineering required to tune a macroscopic object or build the necessary detector seems to violate fundamental principles like decoherence. It's orders of magnitude beyond even QPS concepts.
And maybe the biggest hurdle of all, you mentioned this earlier, it implicitly assumes we have a working theory of quantum gravity, right? And that it behaves in this very specific resonance-friendly way.
Exactly. It presumes a unified framework connecting quantum fields and space-time vibrations exists, and that it allows for these unique, stable, detectable signatures. But finding that theory of quantum gravity unifying general relativity and quantum mechanics that's still perhaps the single biggest unsolved problem in all of fundamental physics, the premise assumes a solution we don't have.
So scientifically, it looks pretty implausible.
Highly implausible based on current knowledge. But despite that, the sources also suggest this thought experiment isn't useless. It's almost like a noble failure. Because the core idea resonates, doesn't it? It connects with very old philosophical ideas, this intuition that the universe is fundamentally vibrational, interconnected like a great symphony.
Music of the spheres kind of thing.
In a way, yeah. And the physics we've explored actually gives a modern, precise language to some of that intuition. Particles are excitations of fields. Matter is a form of condensed energy, frozen music, as some might say. Spacetime does hum with gravitational waves and quantum energy.
And I thought it was really fascinating how the idea of a location's signature being a record of its past connects to modern physics ideas about information.
Yes. The idea that maybe information is more fundamental than matter or energy. Concepts like the holographic principle, which suggests that all the information in a volume of space might be encoded on its boundary. It hints that the universe could be seen as a vast information processing system. In that light, this hypothetical VPS is less like a radio tuner and more like some kind of ultimate cosmic information decoder.
Which is a mind-bending idea in itself.
Absolutely. So even though we have to conclude the system itself is likely impossible, this deep dive, this whole thought experiment, turns out to be incredibly productive.
Yeah.
It forced us to really engage with and hopefully clarify some of the deepest, weirdest, most fundamental concepts we have about reality. The nature of space, time, particles, fields, measurement, information, and the underlying unity of everything.
So the journey was definitely worth it, even if the destination isn't reachable. And maybe that's the final takeaway for you listening. Even the most speculative questions, the ones that seem like pure sci-fi, like navigating by universal vibrations, they can actually be incredibly powerful tools. Tools for deepening our understanding and our appreciation of just how strange, how complex, and how ultimately interconnected reality truly is. So what new questions does this deep dive spark in you about the true nature of vibration, or maybe information, in our universe? Something to think about.